Hello, everyone. And today, I was doing some physics, and I just wanted to talk a little bit about the fundamentals of a black hole. Now, actually, when I was going to the University of Michigan, our final, or my final classes at the university were in Einstein's theory of relativity, and we actually stopped at that point. So one of the later classes that I was taking, the kind of like the final step was Einstein's theory of relativity, which is E equals mc squared. It's how we put a definition onto how we measure energy. And a lot of people are actually confused of what the theory of relativity says. Energy is simply a way we measure the how fast something moves and when it becomes energy as it moves through space or a space. So energy is simply the mass of an object times the speed of light squared. So if I was moving through space and I have a specific amount of mass, but I was moving at the speed of light squared, I would then develop into an amount of energy moving through that space. But today, we're going to talk a little bit about what I know about black holes. So, today we're going to be using the sun, our own sun, as an example if it were to collapse in on itself and create a black hole. So I wrote down some of the formulas because when I attended U of M, we were always allowed a piece of paper, a small note card or something to write down the formulas because we never had to memorize them. And the reason because of that was that if you were working a job or were a physicist day by day, you basically didn't have to really memorize the formulas. But it ended up getting to the point where you used them every day, even in class, that the note card was just basically useless anyway, because you used the note card, or I'm sorry, you used the equations like 1,000,001 times anyway. You didn't even really need the note card. But I'm so washed up in that I haven't been using the equations millions of times a day anyway, so I need a refresher on the equations. But anyway, the main purpose is that we're going to figure out the velocity that the sun has when it collapses in on itself and how far you need to be to get sucked into the black hole and what the velocity of the black hole is when you reach the event horizon. So, the equation actually is V equals 2 times the universal gravitational constant times the mass of whatever's being sucked in over the radius of the black hole. Sorry. So when we look at mass, and I made a mistake right there, we're not actually talking about the mass of the object. That's a big mistake. We're talking about the typical mass of a black hole. And I actually had to look this up because there's about 4 or 5 different types of black holes. But the mass of the most common type of black hole that we have is generally 6 times 10 to the 30th power in kilograms. Now there's one more thing. When I was taught the mass of a black hole and its radius, we, for some reason, and I don't know where this term came from, I used to call it the Schwartz factor, but it's not called that. So I don't know where that term came from, but that's like neither here nor there. What I'm talking about now, and we're moving on from the mass, because I already told you what the generic mass for a regular black hole is. We're going to talk now about the Schwarzschild radius. And you're thinking about, okay, what's a radius? The radius is a dimension we use for circles to figure out where the center of a circle is. So if you have a general circle, think of my hand, we want to find the middle point of this circle. But we don't want to find the whole length of this circle, like the very middle, but halfway in. That's a radius. Now, if we wanted to find the entire length of the inside of this circle, that would be a diameter. And that's something probably most of you guys know of. But the radius would just be halfway. So the Schwarzschild radius is the halfway point of a black hole and the radius around that circle. And why is this important? That's because any object, including you and me, is possible to become a black hole. That's right, you heard me right. Anything. You can become a black hole. The book you're reading can become a black hole. The phone I'm using can become a black hole. We just have to factor in what its Schwarzschild radius is. Now, typical black holes wouldn't ever become you and me. And the reason is because the Schwarzschild radius is directly proportional to the mass of that black hole. And what that means is that as you increase the mass of an object, the likelihood of a Schwarzschild radius increases as well. Meaning that while you and I have the probability of becoming a black hole, it's negligible, meaning it's in the negative. It's a negative number, meaning that while it's proportional to mass, yes, that's correct, it's in such a negative value that it would never really ever happen. I could calculate it out using physics, but it's such an infinitesimally small number that it just wouldn't work. I need a drink of water. I'm sorry, guys. Please excuse me. If I can get it open. What the fuck? Oh no, it's spilled. Oh yeah, that's me. Oh well, it's just water. I had it under my arm, and I wanted to hold the camera at the same time. Just a little bit. Sorry about that. Anyway, it's really dry, and I'm still sick from the flu I had. And now other people in the freaking apartment building have the flu. Ugh. Anyway, the radius. Back to the Schwarzschild radius. It literally is just the radius to tell us what you need to become a black hole, like I was saying. And it's proportional directly to mass, yada, yada, yada. What else? What am I thinking of? Oh, yeah. Moving on. Once you find the radius, you know what something needs to become a black hole. Now, this radius is actually measured in kilometers. So once you find the radius of this object, once it's compressed down, because think about it, when a star collapses in on itself, all that mass is compressing down to a single point. But even though it's compressed down to a single point, we can still measure that object's radius, because you can generically draw a circular structure around anything, right? But the mass of that star that has collapsed in on itself still retains all that mass. It just collapses in on itself to a singular point. So once you figure out the radius it needs, then you have a black hole. But there's a bit of a caveat onto that. All stars rotate. But when they collapse, the period of their rotation increases. What does that mean? A period of a rotation is a full rotation. So you might think that because the sun collapses and it goes into a point that, oh man, how's that going to rotate? It just collapsed in on itself. It's obviously not as circular as it once was before. That doesn't matter. What matters is that it's still rotating. And once it collapses in on itself, it actually is going to rotate much, much faster. And what happens here, what the physics says, is that it's a conservation of angular momentum. What that means is that it's a buildup of specific momentum. So momentum tells us the strength behind that rotation. It's almost like a buildup of potential energy. Potential energy and kinetic energy. Kinetic energy is when you're actually moving. Potential energy is the buildup before it moves. So let's think about this for a second. If I have a rifle, okay, and before I shoot that rifle, how far is it going to go? The potential energy of that bullet is the amount of energy stored up in that gun. And then once it's shot, that's the kinetic energy. And it's the same thing with these black holes. But the difference is that these black holes have such a strong velocity on their event horizon, meaning that they have such a strong force in their velocity where they suck in, that not even light, the speed of light, is bent. And that can't even escape the event horizon, because that's how fast these stars rotate when they become a black hole. Anyway, let's see more. I did more physics on the back. Now, we need to find the velocity. But there's a few orbital mechanics we can work out in physics, because it's our sun, right? Now we're going back to the whole of the sun. Things about, I wrote down a few numbers. A lot of it is really self-explanatory. It's just so I don't get the physics wrong. We know the sun completes its rotation in 25 days. The radius of our full sun is 700,000 kilometers. Let's solve for the sun's Schwarzschild radius. The equation is Rs equals 2 times the gravitational constant times its mass times the speed of light squared. Math. Well, excuse me. You work out the math, and it's really easy. It's literally just cross multiplication. So 2 times that, times the speed of light squared. See, we even factor in the speed of light squared into this radius. That's how strong, or how much this radius is factored into. What we come to figure out is that the radius of our sun is around 3 kilometers. However, it's 3 kilometers. Let's just stick with that. There's another thing we can approximate, that if you really wanted to go all out, we know that the 3 solar mass stellar core of this black hole will end up being 9 kilometers, but that has a lot to do with other different factors, and I'm not even really going into it, because when I looked it up, it had a lot to do with the emission of the black hole, the density of the emission, and stuff that I really didn't have numbers for, because I didn't know how to phrase my question or even how to formalize a thought of where I was even going with that information. I couldn't even figure out when I did that type of physics to figure out the 3 solar mass stellar core, what part of the black hole they were even talking about. So if I ever come back to this problem again, I'm probably going to email like one of my old professors and be like, what were they talking about here? Because I couldn't find anything about it. Anyway, let's move on. Okay, so we know the radius. And now we want to find the black hole's velocity. And remember, the radius was 3 kilometers. Okay, so going back to what I was saying. Okay, the sun completes its rotation every 25 days. Again, the radius of 700,000 kilometers. Radius of the black hole, it's 3 kilometers. Blah, 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 blah. Okay, here's another thing we've got to figure out. We need this is something you might overlook. Because of all that angular momentum, and the sun is collapsing in on itself, it literally shrunk to a black hole. We can figure out, because it collapsed in on itself, and because the black hole has a lot of angular momentum, we can surmise, because there's an angular rotation, there's angular displacement occurring. We can do this because we can derive from the expression based on the fact that it's rotating, that it collapsed in on itself. There must be angular displacement. We get that by dividing the distance traveled along a circular path by the radius. So it's literally based on the natural state of the sun, because it was already happening before. And the sun will tell us this answer because we're looking right now at the original aspect of the sun before it collapsed, because all this angular momentum has now occurred when it dropped into as a black hole. So it would be 3 kilometers. Okay, the radius of the black hole divided by the radius of the original sun, 700,000 kilometers, times 25 days, the 24 hours of the Earth, and 3,600 seconds. Now we figure out the actual period and rotation of the black hole is 9 seconds. We're literally going through what was once 25 days of a full period of the sun to 9 seconds. A period rotation of the black hole is 9 seconds compared to the sun's original 25 days. So now that we know that, and know that it's going through an intense, rapid rotation, what is the sun's escape velocity? The escape velocity is the velocity you feel as an object as you enter the event horizon. It's also the velocity you feel as a photon ray, which is what we refer to as light. A light ray is a photon. So if we do the math, velocity is 2 times 6.67 times negative 11 to the negative 11th power. That's just the gravitational constant. 2 times 10 to the 30th, which we already figured out was I'm sorry, it's not 30th. It's 10 to the 20th. Yeah. We actually, yeah, it's 10 to the 20th. But I'm trying to figure out where I got that number. Oh, where did I get that number? Okay, never mind. I know where I got that number. That was way back. So I actually had to look that one up. What is the mass of the sun? You can't really... Yeah, that's the mass of the sun. All right, I'm sorry. Let's do a redo. Going back to the sun's escape velocity. The original equation, let me just rephrase this. Velocity is 2 times the gravitational constant times the mass divided by r and the square root of that. What is the sun's escape velocity? We know 2, just a number in there in the equation. Gravitational constant, the mass of the sun, and the radius of the black hole. So it would be 2 times 6.67 times 10 to the negative 11th power. That's the gravitational constant. The mass of the sun is 2 times 10 to the 30th kilograms divided by the radius of the black hole, which is 3 kilometers. Going that out, we have the velocity as 9.43 times 10 to the 9th meters per second. Let's scroll back a little bit. How strong or how fast is the speed of light? 3 times 10 to the 8th meters per second. How strong is the velocity of the event horizon? 9.4 times 10 to the 9th. That's why light cannot escape the event horizon, because the velocity of this black hole is stronger than the speed of light. I heard also, from when I was looking this up, that everything is sucked into a black hole. That is completely false, because one of the laws of physics says that matter cannot be created nor destroyed. That is the theory behind matter. You cannot create nor destroy matter. So the article, or the physicists that wrote that everything is sucked in and destroyed in a black hole, is completely false. Because what we are learning recently through different articles I've been reading on my scientific journals is that actually the objects or the space dust or whatever have you that gets sucked into a black hole is actually emitted out by radiation. So in that effect, it holds true that matter cannot be created nor destroyed, because everything that's sucked into that black hole, it's not destroyed. Part of it, or a measure of that amount of information, is emitted back out of the black hole as radiation. And with you, I'd like to say thank you for watching my video. Bye.